Hi there. We're going to finish off what we're covering from Chapter 4 in Schroeder's Thermal Physics by talking about real engines. Now, I have to tell you, full disclaimer here, we're not covering all of Chapter 4. We're going to cut it off here. And I'd also like to say that I took some resources from Thompson Higher Education for this lecture. Okay, so gasoline engines, the planet's handicap, I guess, right now. Here we go. In a gasoline engine, you have 6 processes that occur during each cycle. And for a given cycle, the piston moves up and down twice, and this represents a 4-stroke cycle. Now, the processes in the cycle can be approximated by the Otto Cycle, named after the engineer, the German engineer Otto, who came up with this. Now here is a PV diagram of an Otto cycle, shown here at the right. The Otto cycle approximates those processes that occur in an internal combustion engine. Now, of course, the real engines are going to be less efficient than this idealized construct here. Basically, the Otto cycle includes 2 adiabatic processes and 2 isovolumetric, or so-called also isochoric processes here. So let's go over each one of these in detail. So basically, it starts off here, you have the intake, and then you have the compression, the spark, the power stroke, and then the exhaust stroke. Now, if you'd like to see this in action, I have a link down here to another YouTube video which shows you what's happening in an animation inside the engine. I'm just going to go through it step by step and talk about the theory. So during the intake stroke, what happens is the piston moves downward while a gaseous mixture of air and fuel is drawn into the cylinder. In this step, energy enters the system as potential energy in the fuel that's injected along with the air. This is step O to A here in this Otto cycle, so it's kind of along the bottom and gets us ready to start the cycle at point A. Now, in the next step, it's called the compression stroke. The piston is going to move upward, and that compresses that air-fuel mixture adiabatically, which of course means quickly. When this happens, PV is equal to nRT, and so the temperature is going to rapidly increase. The work is done on the gas, and it's positive, and it's equal to the negative area under that curve. And this is step A to B in the Otto cycle here, where it's going up along that adiabat. The blue lines here indicate isotherms, and remember that adiabats are steeper than isotherms. Now what happens next is the spark. There's a spark plug, and combustion occurs when that spark plug fires. This isn't really one of the strokes of the engine. It occurs very quickly while the piston's at its highest position. At that point, there's a conversion from the potential energy in the fuel, the chemical energy in the fuel, to internal energy. This is step B to C. It happens really fast, and so you can approximate that as isovolumetric because it happens so fast. Next comes the power stroke. In the power stroke, the gas expands adiabatically. Basically, the gas-fuel mixture exploded, and it's rapidly expanding outward. This causes a temperature drop, and the work is done by the gas. That's why it's called the power stroke, because this is where the power of the engine comes from. Now the work here in C to D is equal to the area underneath that curve. So the work done by the engine would be the work done from C to D, the area underneath C to D, all the way down to the axis here, subtracting off the work from A to B, which would be the white area under the curve from under B to A. So if you subtract those two numbers, then you're going to get the work done by the engine. And that's because steps BC and steps DA are isovolumetric, and for those steps, the work is 0. Okay, next step in the process is the valve opens, and then the exhaust valve opens, which allows that spent fuel air mixture to exit. This is the exhaust step. So the pressure is going to suddenly drop there. The volume is going to stay pretty constant, so no work is done, and energy begins to be expelled from the interior of the cylinder. And then you have the exhaust stroke, where the piston moves upward while the exhaust valve remains open, getting rid of residual gases, expelling them to the atmosphere, and the volume is going to decrease. Okay? So that's step A to O in the Otto cycle, so it's getting ready. And then of course the cycle will start all over again, drawing in fresh air and fuel for the next cycle. Now, if the air-fuel mixture is assumed to be an ideal gas, then you can write the efficiency of the Otto cycle this way. The efficiency is equal to 1 minus V2 over V1 to the gamma minus 1 power. Okay, so gamma is that ratio of the molar specific heats, that adiabatic exponent that we talked about earlier in, I think it was chapter 1 in Schroeder's thermal physics. V1 or V2, V1 divided by V2 is called the compression ratio. So typical values are compression ratios of about 8, gamma for 1.4, and efficiencies of about 56%. So this is the theoretical Otto cycle, but real efficiencies are somewhere like 15 to 20%. And those losses are mainly due to friction, energy transfer by conduction, incomplete combustion of the air-fuel mixture, amongst other issues. Okay, another engine that I'd like to talk about are diesel engines. Now these are very, very similar to Otto cycle engines, but they don't have spark plugs. They can get away with not having spark plugs because the compression ratios are much greater. And also the fuel that diesel engines use is slightly different than the Otto cycle engine fuel. So the compression ratio is greater, and so the cylinder temperature at the end of the compression stroke is a lot higher. So that when you inject the fuel, the temperature is already high enough that the mixture ignites spontaneously just due to the temperature without that spark plug. Now, diesel engines are more efficient than gasoline engines because of the larger compression ratios, but for a given ratio, the diesel engine would be less efficient. If you'd like to see a video of diesel engines at work and animation, I highly suggest that you check out this YouTube video link that I have right here. Okay, so what happens there is that along this bottom line, kind of pre-step 1 there, air is injected into the cylinder, and then it's compressed from step 1 to 2. Once the air is compressed fully, then the fuel is sprayed in as that piston moves out at a rate so that the pressure is constant. That's step 2 to 3. At that point, the temperatures are high enough that the fuel ignites spontaneously, and then you have your power stroke where the piston is pushed down by that exploding fuel, which has a rapid expansion from 3 to 4. And then the spent fuel air is vented, which is step 4 to 1, and the efficiencies for that cycle are given here. It's a much more complicated formula than the Otto cycle efficiency. The efficiency is equal to 1 minus 1 over V1 over V2 to the gamma minus 1 times V3 over V2 to the gamma minus 1 divided by gamma times V3 over V2 minus 1. Okay? Yet again, the compression ratio is given there. You can see that it's governing what the efficiency is. And also gamma is that adiabatic exponent, which would be about 7/5 for air. Now, another typical type engine that people like to talk about is Stirling engines. In 1860, Robert Stirling, who was a Scottish clergyman, patented the Stirling engine, and it's found a wide variety of applications ever since then. In a Stirling engine, fuel is burned externally to warm one of the engine's 2 cylinders, and a fixed quantity of inert gas moves cyclically between the cylinders, expanding in the hot one and contracting in the cold one. A Stirling engine is easier to manufacture than an internal combustion engine or a turbine, and it can run on burning garbage, for example. It can run on the energy of the sunlight and produce no material exhaust. So I have an example problem based upon the Stirling engine that I'd like to work for you. So here's a PV diagram for a Stirling engine. You can see that it has 2 isothermal processes and 2 isovolumetric, also called isochoric processes. So in this engine, or in this problem, you have n moles of an ideal monatomic gas being taken through the cycle of these 2 isothermal processes, which are occurring at temperatures 3 Ti and Ti respectively. And also 2 isochoric processes that are occurring at volumes Vi and 2Vi respectively. So determine in terms of the number of moles N, the gas constant R, and that temperature Ti, what the net energy transferred by heat to the gas would be, and also the efficiency of the engine. So remembering that you've got those two isothermal processes and the two isovolumetric processes, let's go over steps here. So for step 1, the work is equal to 0. Step 1, I'm going to call that isovolumetric process that takes place at volume V sub I. So at that point, the work is equal to 0, and the change in the internal energy of the gas would therefore, by the first law of thermodynamics, be equal to Q1. Now, the change in the internal energy of an ideal gas could be written as, for a monatomic gas, 3/2 times nR times delta T. Okay? This is due to the equipartition of energy theorem. So the change in the temperature is going between isotherms Ti and 3Ti. So if you're trying to take a delta of that, then the delta T would be 2 times Ti. So the heat, which is equal to the change in the internal energy of the system, because the work is 0 for an isovolumetric process, that heat that enters the gas during step 1, that isovolumetric process, is 3/2 nR times 2 Ti. Now, heat would also enter in step 2, which is the isothermal process that takes place at temperature 3 Ti. So for an isothermal process, the change in the internal energy of the system is equal to 0, which means that the heat is equal to negative of the work. Now, in an earlier discussion, we found what the formula was for the work for an isothermal process. The work for an isothermal process is nRT times the natural log of the initial to the final volume. So minus the work would be minus nR times the temperature, which would be 3 Ti, times the natural log of the ratio of the initial to the final volume. The initial volume is given as Vi, and the final volume is given as 2Vi. So your heat would be equal to negative 3 nRTI times the natural log of 1/2. Now the total heat energy taken into the system would be taken in steps 1 and 2, where you have that upward isovolumetric process followed by that isothermal process at 3 Ti. Summing those two things, you get 3 nRTI times 1 minus the natural log of 1/2. And that gives you 5.08 nRTI. Okay, so that's the heat. So that solves the question for part A, what heat energy enters the system. Now we also need to solve for the efficiency of the engine. Remember, the efficiency is the work over Q sub H for an engine. So we have to find the work of the engine. Now, the work in a cyclic process is the area enclosed by the curve. To remind you really quickly, here you had this cyclic process, and you have an isothermal process at 3 Ti and an isothermal process at Ti. The work is that beige area enclosed by the curve. If you subtract the work done at temperature Ti from the work done at 3 Ti, then you get that enclosed area, okay? The isovolumetric processes don't count because the work for those steps is 0. So I'm going to do that here. The work done by the engine would be the absolute value of work 2 minus work 4, all right? So if I solve for that, then I get 3 nRTI times the natural log of 2 minus the natural log of 1/2, all right? Now that's because, of course, those are isothermal processes, and so the work for each one of those is going to be nRT times the natural log of the initial over V final. So I'm plugging in for that. The 1/2s and the 2's come from the fact that the ratio of the initial and the final volumes will be either 2 or 1/2, depending on which way you're going, because the volume goes from Vi to 2Vi or vice versa. So plugging in for that, I get 3 nRTI times the natural log of 2 minus the natural log of 1/2. I get 2.77 nRTI for my work. Now the efficiency of the engine will be the work divided by Q sub H, which is 2.77 nRTI divided by 5.08 nRTI, which gives me 0.55. So the engine's efficiency is 55% theoretically for that Stirling engine. Okay, that concludes our discussion of real engines, our theoretical discussion of real engines, of course. I haven't really even scratched the surface on the physics and engineering of these systems. But at least it's an introduction. So I hope you enjoyed that. We'll be stopping chapter 4 there for our class. See you in class.